Imagine buying a 100 amp hour battery only to find out that when you actually use it, it only gives you about 70 amp hours, maybe even less. Well, it's not exactly a scam, it's just how batteries sometimes work under certain conditions. And if that happened to you, it's probably because you overlooked this, a rating on your battery that says something like 10 hours or 0.1 C. That's the C rating of your battery, and if you don't know what that is, this video is for you. A C rating is a specification that tells you the maximum rate at which a battery can be discharged while still delivering 100% of its advertised capacity. In other words, it defines the maximum current draw at which the battery's amp-hour rating is actually accurate. Let me break it down. This rating is usually provided using the letter C, short for current, which is where the name C rate comes from. You'll often see a number next to the C, either before or after it, but mostly it's just given in hours. Consider a lead-acid battery that's rated at 100 amp hours, for example. Most lead-acid batteries are rated at either a 10-hour or 20-hour C rate. So when you see ratings like 0.1 C, C10, or just 10 hours, they all mean the same thing. If one of those ratings was printed on the battery, it would mean this. To get the full 100 amp hours out of it, the battery would need to be discharged over a period of no less than 10 hours. In other words, the advertised 100 amp hours capacity is only accurate if the battery is discharged at 10 amps or less. Now let's say the manufacturer gives a rating like 0.05 C, C20 or 20 hours. That means to get the full 100 amp hours, the battery should be discharged over 20 hours or at no more than 5 amps. So if your C rating is written as a decimal before the letter C, just multiply that number by the battery's amp-hour rating to find the rated discharge current in amps. If it's written as a number after the letter C or is given in hours, then you divide the amp-hour rating by that number to get the discharge rate in amps. So why are these ratings something you should actually pay attention to? Well, because generally speaking, the faster you discharge a battery, the less usable capacity you'll get out of it. Let me show you what I mean. Here's a table from the datasheet of a 12-volt 100 amp hour lead-acid battery rated at C10, meaning it's rated to be discharged over 10 hours or at no more than 10 amps. If we look here, we see that when the battery is discharged at 10 amps, it lasts for 10 hours. So as advertised, you get the full 100 amp hours. But now let's double the current and discharge the battery at 20 amps. You would expect it to last for 5 hours, right? Since 100 amp hours divided by 20 amps equals 5 hours. But no, it only lasts for 4 hours. Multiply that by the discharge current and you're only getting 80 amp hours of actual usable capacity. And if we keep increasing the discharge current, the capacity drops even further. For example, according to the datasheet, if you discharge the battery at 55.6 amps continuously, it only lasts 1 hour. That gives you just 55.6 amp hours, which is almost half the rated 100 amp hours. So to recap, at 10 amps you get 100 amp hours, at 20 amps you get 80 amp hours, and at 55.6 amps you only get 55.6 amp hours. This effect is known as Peukert's law, and it mostly applies to lead-acid batteries. See, some of the chemical reactions happening inside the battery along with the physical components that make up the battery can be modeled electrically as an internal resistance. And because of Ohm's law, this means the more current you draw from the battery, the greater the voltage drop across its terminals is going to be. But here's the thing, this internal resistance isn't fixed. It actually also changes depending on other factors. For example, it increases as the discharge current goes up, and it also increases as the battery gets closer to being fully discharged. All of this creates a kind of chain reaction. The higher the current and the lower the state of charge, the faster the voltage drops. And since battery voltage is the indicator we use to estimate how much charge is left, that drop in voltage makes it look like the battery is empty sooner than it actually is. So the battery hits its cutoff voltage earlier and has to be disconnected, even though it still has some chemical energy left inside. Now, if you don't have access to a table that estimates the effective capacity of your battery at different discharge rates, you can actually estimate it using Peukert's equation. Here's the basic formula, and it can also be written in a few different ways. So all you need is the Peukert constant, which depends on the battery you're using. The problem is manufacturers don't typically provide the specific Peukert constant for their batteries. So I did some digging and some calculations, and here's a good rule of thumb. Use 1.25 for AGM batteries, 1.3 for gel batteries, and 1.4 for flooded lead acid batteries. So let's say for example you have a 100 amp hour AGM lead acid battery with a 0.05 C rating, equivalent to a rated discharge time of 20 hours. And let's say you plan on discharging the battery at a constant rate of 15 amps. You can estimate the effective capacity like this. Now to find out how long the battery will last, just divide the effective capacity by the discharge current. For lithium batteries, the situation is a bit different. These batteries are much better at maintaining their capacity even at high discharge rates, and that's due to their chemistry, which results in a much lower internal resistance. This means that if you discharge a 100 amp hour lithium battery at 100 amps, it will still last about 1 full hour, delivering its full rated capacity except maybe for a couple of amp hours. So while Peukert's law still technically applies to lithium batteries, the Peukert constant for these batteries is very close to 1, making the effect negligible in typical systems. That being said, most lithium batteries used in solar applications are equipped with a built-in battery management system that provides discharge over current protection. So if a 100 amp hour battery tries to discharge at 100 amps or more for long enough, the BMS will shut it down. And typically the reaction time will depend on how high the discharge current is. For example, for this EG4 48 volt 100 amp hour battery, the datasheet specifies that if the current is between 102 and 150 amps, the BMS will shut it down in 30 seconds. If the current is between 150 and 300 amps, the BMS shuts down in 3 seconds, and if the current exceeds 300 amps, the BMS reacts in under 0.1 milliseconds. These overcurrent protection measures aren't there to prevent capacity loss, they're there to prevent overheating, damage, or thermal runaway. When designing and sizing the battery bank in an off-grid setup, the focus is usually on energy capacity, how many watt-hours the system needs. But if you're using lead-acid batteries, it's also important to double-check whether the battery bank can still deliver the required discharge current for your loads while still maintaining the desired capacity. Even if your battery bank technically has enough capacity to power your appliances, there may be cases where you need to add more batteries, not for extra energy storage, but just to account for Peukert's law. For example, let's say you want your battery bank to run an induction cooktop for a total of 1 hour per day, and the cooktop uses 1200 watts. That means that it would consume 1200 watt hours per day. And for simplicity, let's just ignore the inverter losses and the other system inefficiencies for now. Well, a single 12 volt 100 amp hour battery has a capacity of 1200 watt hours. So will that be enough? The answer is no. Because if we try to run the cooktop on a single battery, the battery would be discharging at a 1 C rate. For instance, if we refer back to the table from our earlier example, we can see that if the battery is discharged over 1 hour, it only provides 55.6 amp hours of usable capacity. But at 12 volts, we need the full 100 amp hours to reach 1200 watt hours. So one solution to this would be to add another battery, which would give us a little more than the 100 amp hours that we need. However, remember that lead-acid batteries shouldn't be discharged below 50% if you want to maximize cycle life. That means we would need at least 200 amp hours of effective charge capacity at 12 volts to meet our needs and to stay above 50% depth of discharge. The first instinct might be to just add 2 more batteries to double the size of the battery bank. However, the more batteries you add, the lower the discharge current on each battery will be, which in turn means more effective capacity. So if we really want to optimize for cost and avoid oversizing, we might be able to get away with just 3 batteries instead of 4. For example, based on the same table, at a discharge current of 34.6 amps, each battery would last 2 hours, which means an effective capacity of 69.2 amp hours per battery. With 3 batteries, that gives us 207.6 amp hours of effective capacity. And since the 100 amp load is now shared between the 3 batteries, each one would only need to provide 33.3 amps, which is lower than 34.6, so we can expect a little bit more than the effective capacity we just calculated. Now, keep in mind that C-rate doesn't just affect capacity, it also affects the battery's lifespan. Higher discharge rates put more stress on the battery and accelerate degradation. So, optimizing for depth of discharge alone might not be enough, and you may still need to add more batteries just to reduce the discharge rate, which can quickly become very impractical. This is one of the main reasons why, in many cases, lithium batteries just make more sense, especially in setups where a high C rate is required. For this particular setup, a single 12V 100 amp hour lithium battery would be enough to get the job done. And it would significantly simplify the process of sizing the system, it would make it safer, it would make the battery bank at least 3 times smaller in size and 9 to 10 times lighter, and it would reduce costs by half. That's it for now. I hope you guys have a much clearer understanding of C ratings and their implications on your system after watching this video. If you do, give it a thumbs up so more people can find it, and subscribe to the channel to see more interesting videos like this one. If somehow this left you more confused, feel free to leave your questions in the comment section and I will gladly answer them for you. Thank you very much guys for watching, and I'll see you in the next one.